Welcome to this video on series and parallel circuits. We will cover how components connect, how current and voltage behave, and how to tackle exam questions with confidence. In this video, we will walk through 4 key sections: defining series and parallel circuits, understanding how measuring instruments connect, and reviewing essential exam tips to help you succeed. Chapter 1. Series circuits. In a series circuit, there is only one loop and one path for the current to follow. Every component shares the journey. What is a series circuit? Think of it like a single train track. The current must pass through every component in sequence. If any part of the path is blocked, the entire flow stops. When it comes to current in a series circuit, the key rule is that it remains the same at every point. Because there is only one path, the same number of charges flow past every point each second. In a series circuit, the total potential difference is shared between components. The sum of voltages across each component equals the total supply voltage. Larger resistance means a larger share of the voltage. Adding components in a series circuit increases the total resistance, as it is the sum of all individual resistances. Consequently, this leads to less total current flowing through the circuit. A major weakness of series circuits is that a single break stops everything. If one component fails, the entire loop is broken and all components switch off. To summarize series circuits, they have one loop, the current is the same everywhere, voltage is shared, and one failure shuts down the entire circuit. Chapter 2. Parallel circuits. These circuits feature multiple branches and independent components, representing how most real-world electrical systems are wired. In a parallel circuit, components are connected on separate branches. Current reaches a junction and splits, providing independent paths. This allows components to operate separately from one another. Think of current in a parallel circuit like a river, splitting into separate channels. The total current leaving the battery equals the sum of the currents flowing through each branch. Unlike series circuits, the potential difference across every branch in a parallel circuit is the same and equal to the supply voltage. Each branch receives the full voltage. Because branches are independent, removing a component on one branch has no effect on others. This is why if one light in your house goes out, the others remain on. Interestingly, adding more branches to a parallel circuit actually decreases the total resistance because current has more paths to follow. Remember this, as it is a common exam trap. Let's review the parallel circuit summary. Key takeaways are separate branches, current that splits at junctions, uniform voltage across each branch, and total resistance that decreases as you add more paths. Moving on to Chapter 3. Real-world applications. Understanding why we use parallel circuits in our homes explains why your appliances can operate independently of each other. Homes use parallel circuits so every socket and appliance receives the full mains voltage. This ensures that turning off one device doesn't stop others from working, and it lets you easily add new appliances. Here is a head-to-head comparison between series and parallel circuits. Keep this table in mind for your exam to distinguish between their properties regarding paths, current, voltage, and resistance. Chapter 4. Measuring instruments. Learning to connect ammeters and voltmeters correctly is essential. Using them the wrong way around is a common and avoidable mistake. The ammeter measures current and must always be connected in series. An ideal ammeter has zero resistance to ensure it does not disturb the circuit's total current flow. The voltmeter measures potential difference and must always be in parallel. An ideal voltmeter has infinite resistance, ensuring no current is drawn away from the component being measured. Use this quick reference guide to remember. Voltmeters go vertically across a component in parallel, while ammeters go along the wire in series. Note their distinct symbols as well. Chapter 5 covers circuit diagrams. These provide a standardized visual language that allows physicists around the world to interpret circuits unambiguously. Standard symbols are vital for clarity. Learn to recognize the symbols for cells or batteries, lamps, resistors, and switches. Each has a specific purpose and representation in a circuit diagram. To read a diagram, trace the path from the positive terminal to identify series components. Count the junctions to find parallel branches, and always double-check your meter placements. Chapter 6 looks at combined circuits. Many practical setups are not purely series or parallel, but use a hybrid of both to achieve specific control or functionality. Combined circuits let you control a bank of parallel branches with a single switch or fuse in series. To analyze these, break the circuit into smaller, manageable sections. Follow this step-by-step approach. Identify the series parts, locate the parallel sections, apply the appropriate rules for each, and then combine your findings to solve the circuit. Finally, Chapter 7 focuses on exam skills. Mastering these rules and avoiding common pitfalls will help you perform your best in your physics examinations. Let's review the golden rules for your exam. Remember that for series circuits, current is constant, and voltage is shared. In parallel circuits, voltage is identical and current splits. Always place your meters correctly. Avoid these common exam traps. Do not confuse current and voltage rules. Be aware that adding branches in parallel actually reduces total resistance, and always verify your meter placement. Ammeter in series, voltmeter in parallel. Here is a worked example for a series circuit. With two resistors of 4 and 6 ohms in series with a 12-volt battery, the total resistance is 10 ohms, leading to a circuit current of 1.2 amps. Now for a parallel example. Two resistors of 6 and 12 ohms are in parallel with a 12-volt supply. The total current is found by summing the individual branch currents, resulting in a total of 3 amps. Test yourself with these 3 practice questions. Calculate the current for a series circuit, find total current for parallel branches, and explain home wiring principles. Pause the video to solve them. Here are the answers to our practice questions. Check your calculations against these results and ensure you understand the reasoning behind each, especially why home circuits operate in parallel. Refer to this key vocabulary list during your revision. Understanding terms like potential difference, resistance, and the definition of a circuit junction will give you an edge in your exam. These are the essential formulae you must memorize. Ohm's law, the additive nature of resistance in series, the division of voltage in series, and the summing of currents in parallel are your core tools. Study this final cheat sheet. It summarizes everything we have covered today. Mastering this comparison is the key to answering the majority of circuit-based questions on your GCSE Physics exam. You are now ready to tackle your exams. Remember, series means same current, parallel means same voltage. Keep this mantra in mind, and you will be well prepared for any circuit question.